So, last class I have discussed about the calculation of load carrying capacity of pile by using dynamic equations. Now, discuss I will explain the fourth methods by which we can determine the load carrying capacity of the pile, and that is based on the penetration or the data. Penetration means SPT or the CPT data. So, the first one that the correlation with the penetration test data, and we have discussed the standard cone penetration test and then the static standard penetration test SPT or the static cone penetration test or the dynamic cone penetration test. So, as I mentioned in the cone penetration test, static cone penetration test, we can separately determine the tip resistance and the friction resistance. So, in case of pile, this SCPT data is very useful to determine the load carrying capacity of the pile. So, first I will discuss about the SCPT data and then I will discuss about the standard penetration test data or SPT data. The first, and all these expressions are again valid for the driven piles, okay, in sand, and as I mentioned, these the in situ tests are always useful for the granular soil. So, this also useful for the driven piles in sand. So, remember, so this is driven piles in sand. Okay. So, first the using the cone penetration resistance or the SCPT. So, this static cone. So, for the pile tip resistance, I can determine QPU that is equal to the SCPT resistance, that means the cone resistance. SCPT, this is SCPT, this cone resistance QC, and that is equal to the tip resistance of the pile for driven pile in sand. And which QC will consider? If you look at this figure, the QC, the average QC below the 1D and above the 3D from the pile base, this total 4D zones SPT, average SPT we will consider as these QC. Okay. So, and this D is the diameter of the pile. So, that means the average cone resistance value below the 1D soil from the base of the pile and above 3D soil from the base of the pile, this total 4D soil average SPD average cone resistance will be equal to the tip resistance of the pile. Okay. So, this is for the tip resistance QPU. Now, for the screen friction also we can use by using the cone penetration resistance data and by using the Mayerhof correlation. So, for the displacement piles are nothing but the driven pile, okay, because displacement piles, when I apply the pile is driven, then the soil is displaced. So, this is the displacement piles and the driven piles. There the QC average by 2 will give me the friction resistance Fs, and it is limited to 100 kilonewton per meter square. Remember that, because this value cannot be greater than 100 kilonewton per meter square. If it is greater than 100 kilonewton per meter square, you have to take 100 kilonewton per meter square. And QC average means the average cone resistance along the length of the pile will be considered here as the QC average. And another thing you if you note here that the Fs unit is kilonewton per meter square, but QC average unit is kg per centimeter square, because this way, these are empirical expressions, you have to use the proper unit. So, remember that QC average is kg per centimeter square, but Fs unit is kilonewton per meter square. For H pile or H section pile, this expression is QC average divided by 4 and it is limited to 50 kilonewton per meter square. So, that means here your QS cannot be greater than 100 kilonewton per meter square, and this case QS cannot be greater than 50 kilonewton per meter square. Okay. This is method number 1. So, that is we can get, and then the next method is the IS method. Okay. So, our IS code also recommended that how to calculate the tip resistance and frictional resistance based on the SCPT data. Okay. So, this is the IS code equation QPU, which is the average of QC 0 plus QC 1 plus QC 2 divided by 2. These expression we have to use. Now, let me explain one by one all these three cone resistance. What are the meaning of all these three cone resistance? Okay. So, now QC 0 is the average cone resistance below the twice D soil from the tip of the pile or the base of the pile. That means, we have to consider the soil below the twice D of the from the pile base, and average of the QC value within this twice D zone is QC 0. So, average cone resistance below the base of the pile is treated as QC 0. Then QC 1 is the minimum cone resistance of this zone, twice D zone below the base of the pile, because your QC may not be uniform within this zone. So, we have to take the minimum value of QC within this zone, which will be treated as QC 1 for the minimum cone resistance of this zone. And what is QC 2? QC 2 the average of minimum. Okay, that is a confusing word, but or confusing sentence. This is the average of minimum cone resistance, but let me explain what is that. Okay. So, we will take the 8D zone above the base of the foundation, pile foundation, and then that zone's minimum average of minimum cone resistance we have to consider as QC 2. Okay. So, these are the three meanings. So, I will solve one problem, then I will discuss that what are the actual meaning of these three things. Okay. So, first, and then this is that was the tip resistance or QPU, and the friction resistance IS code recommended that from this different soil your friction resistance should be from this zone to this limit to that limit. That means, if it is clay, then QC average, this QC average is the average penetration along the your length of the pile. So, if you have the QC value, then this will be QC divided by 25, this will be QC within to QC divided by 12.5. So, this range, this is for the silty clay to silty and silty sand, this is for the sand, and this is for the coarse sand to gravel. Okay. So, this is QC is along the length of the pile. This will give you the range of the frictional resistance. Okay. So, let us solve one problem by using two methods that I have discussed. One is first one, then the next one is the IS code recommendation. So, first one, this is one field data of your QC value along with the depth. Okay. X axis is cone resistant QC, it is in megapascal. Okay. So, this is 0, this one is 4, this one is 8, 12, 16, 20. Okay. This is in megapascal, and this is 0, this is 2, 4, 6, 8, 10, 12 and 14. Okay. So, this is the total cone resistance. So, this is the variation. So, what I am doing, I am plotting them in a straight line where the variation is very less. Okay. And if the variation is more, then I will take the separate straight line part. So, that is why from this zone to this zone, this variation is not that much. So, what I am doing, I am taking them as a straight line. Okay. Then from this zone to this zone, again there is a small variation. So, I am taking like this. Then from this zone to this zone, this is the variation. So, I am taking, if you want to calculate it more accurately, you can take more variation, okay? But I think that is fine as per my understanding for this problem. So, then this one I am taking like this, okay? And then like this, and then this one like this, and then this is, and then the bigger one okay, and then this one, this one, and finally this one. So, this is the variation of the QC. This is your QC along the depth. Depth is in meter, and remember that QC is MPa. Now, the example is determine the allowable load carrying capacity of a 11 meter long pile with a 450 millimeter diameter. It is a driven pile constructed in the sand. This is a sandy soil with cone resistance profile as shown in the figure. So, this is the cone resistance profile. So, that I have taken as a straight line wise. Now, I will take all the values based on the recommendation. Okay. So, now the first case that I will discuss is that, so yeah. So, for the method 1 that I have discussed, okay. Method 1, your equation was that QPU is equal to QC, but QC is 1D from the base and that is 3D from the base above the base, 1D below the base of pile, and 3D above the base of pile. Okay, that is the average. Okay. So, pile length is 11 meter and diameter is 450 millimeter. Okay. So, that means the 1D means it is 0.45 millimeter below the base of the pile, and 3D means 3D 0.45 is that this is 1.35 from the above the base of the pile. So, 11 meter is this is the 11 meter. So, where this is the your 10. So, this is the 11 meter where it is cutting. So, this is the point. So, where the pile base is here, because this is the pile base 11 meter. Okay, this is 11 meter. Okay, this is 11 meter. So, this is the pile base. So, the QC from up to the 0.45 meter, 0.45 meter is here. This is 11.45 meter. Okay, this is 11.45 meter, and 1.35 meter means 9.65. This is 9, this is 9.65 is somewhere here. Okay, this is 9.65 meter, because 3D means 1.35 above the pile base. So, 1D means the soil 11 plus 1D, that means 1.45 11.45 meter, and then the 11 minus 1.35. So, that is 9.6. So, 9.65 we are getting 11 minus 1.35 meter. So, that is actually 9.65 meter, because that is the 3D. So, this 9.65 meter to 11.45 meter zone, that QC, this zone's QC average will be the QPU. Okay. So, now let me write this way, that if this is the 0 at the tip, and if this is the QB, okay, 11.45. So, at your depth, I am writing in depth. So, at depth 11.45 meter, your QC value is 20 into 10 to the power 3 kilonewton per meter square. Okay. So, you can see QC value is 20, because 20 is this point, 20 is the QC value, and it is 10 to the power 3 because QC is megapascal. So, I am writing them in kilopascal, that is kilonewton per meter square. So, at 11 meter, the QC value is 10 into 10 to the power 3 kilonewton per meter square. So, this is at 10 meter, this is the 11 meter, your QC value is 10, okay, megapascal. So, that means 10 into 10 to the power 3 kilonewton per meter square. So, from here to here there is a variation, then from here to here there is another variation. So, this value is at 10.5, this is at 10.5. So, at 10.5 meter, QC value is 500 kilonewton per meter square. That means, this is your 0.5 meganewton at this point. So, you can remove this one. So, this is 0.5 meganewton. So, this is 500 kilonewton meter square, and so this is the from here to here one zone, then from here to here another zone, and from here to here at 9.65 meter, QC value is equal to, coming out to be your 5000 kilonewton per meter square, or 5 meganewton per meter square. This is the 5. So, this is corresponding to 5. So, this way you will get the QC value. Now, you take the weighted average. So, the weighted average of QC or QC average is equal to, so what I am taking, first I am taking this zone, this is below the base. So, average value is your 10 into 10 to the power. So, average value I am taking, here it is 20. So, 20 into 10 to the power 3 plus, here it is 10, 10 into 10 to the power 3 divided by 2 is the average, and that length is 0.45. So, it is 0.45. Okay. Then from here, then this length is, here it is 20 into 10 to the power 3, here it is 10 into 10 to the power 3. I am taking the average of this zone below the base of the footing, and that thickness of that zone is 0.45. So, I multiply it by 0.45. Okay. Then from here to here, that average is, you can see from 11 to 10.5, it is 10 into 10 to the power 3 plus 500, take the average, then multiply that thickness is 11 minus 10.5. Okay. And then the next one. So, I have gone from here to here, here to here, and then this one. Okay. Then the last one average is 500 plus 5000 divided by 2 into the that thickness is 10.5 minus 9.65. Okay? And then the total one we have to divide by the total length. Total length is 4D and this is 1.35, 1.35 plus 0.45. Okay? So, that is the total length. Total length is 1.35 plus 0.45. So, we will get the final value of QC average, or this is weighted average, is 6507 kilonewton per meter square. Okay? So, this is the QC average of that zone using the first method. So, if I use this first method, so this will be the QC average that I am getting. Okay? So, now I can write that my P or Q PU is equal to QC and I have taken the average. So, that will be equal to also 6507 kilonewton per meter square. Okay? And then if I multiply it with the area, then I will get that QPU is equal to AB into QPU. Okay. So, finally, if I multiply it this value, so I will get that QPU is equal to pi d square by 4 into 6507. So, that is equal to 1034.4 kilonewton. Okay. So, this is the QPU or the tip resistance I am getting. Now, similarly, you can, if you have, again you draw the same straight line. Now, from 0 to 11 meter, you take the weighted average. So, I have taken this zone weighted average for QP, and if you take the weighted average for entire length of the pile, that will give you the frictional resistance. So, that weighted average of QC average from 0 to 11 meter. So, you take from 0 to 11 meter is here. So, from here you take this value. So, from here you take the weighted average the same way that I have done. If there is a change in the direction of the, or the change in the slope of this straight line, because then you take, this is the one line from 0 to this one zone, then this is another zone, this is 1, this is 1, this is 1, and then up to this 11. So, you take this one, this is average into the thickness, this QC average into the thickness, this QC average into the thickness, then this one QC average into the thickness of this zone, like this you take the average. So, I am not doing this average, you can calculate this for your problem, take the average. So, average value if I do, it is coming out to be 3642 kilonewton per meter square. So, now I will use that Fs is equal to Q average divided by 2 for driven pile, and remember that this Q average is kg per centimeter square. If you now convert it, divided by 100, it will be 36.42 kg per centimeter square. Okay. So, now if I put this value 36.42 divided by 2, so this will give you 18.21 kilonewton per meter square. That I mentioned that your QC average is kg per centimeter square, but Fs is kilonewton per meter square. Okay? And that is less than 100 kilonewton per meter square, because that is the limit. So, okay. So, we can use this value. So, my QF is coming out to be pi d 0.45 into 11 is the length of the pipe into 18.21. Okay. So, that is equal to 283 kilonewton. Okay. So, now QU is equal to 1034.4 plus 283. So, that is equal to 1317.4 kilonewton. So, Q safe is equal to 1317.4 divided by 2.5. So, this is 527 kilonewton. So, this is the total load carrying capacity of the pile, and the QU is safe load carrying capacity is 527 kilonewton. Okay. So, this is the first method. Okay. Now, let me explain the next method, that is the IS code method. Okay. So, I will do the same thing, but here there is slightly difference. Okay. So, I am doing the same one, I am just taking this straight line, this is the straight line, then again this portion straight line, then this is straight line, straight line. Okay. Okay. So, the method 2. That is IS code. The expression is that QPU is equal to QC0 plus QC1 divided by 2 plus QC2 divided by 2. Okay. Now, here as I mentioned that my QC0 is the average of the zone which is that below the 2D zone. So, 2D zone means your, so that means the one, this is the base of pile. So, this zone above we are taking 8D and this zone we are taking 2D. Okay, for this IS code method, and 2D means 2 into 0.45, that is 0.9 meter below the base of the pile, and 3.6 meter above the base of the pile. Okay, 8D means 3.6 meter here, because your D is 0.45 meter. So, now here 0.9 meter. So, this is the 11 meter. So, 0.9 meter will be somewhere here. Okay, 11.9 meter. So, this is 0.9 meter is here. So, this one is 11.9 meter, and this is the 11 meter. So, this is the here 11 meter. So, we have to take the average value, QC0 means average value of this zone. Okay. So, you can take the same way average. Here it is 10,000 kilonewton per meter square, here it is 20,000 kilonewton per meter square, here also it is 10,000 kilonewton per meter square. So, and this zone is 4.45 thickness of 11.45 this zone. So, from here to here it is 0.45 is the thickness. So, the average value will be, I am just doing one, that is 10,000 into 3 plus 20 into 3, and thickness of this zone is 11.45 minus 11, then plus again from here to here also half into 20 into 10 to the power 3 plus 10 into 10 to the power 3, because here it is 10,000, here it is 10 into 10 to the power 3 kPa. Here also it is 10 into 10 to the power 3. Here it is 20 into 10 to the power 3. Okay. So, from 10 to 20 average the thickness, here also the average and thickness will be, it is 11.9 minus 11.45. Okay. So, and the total one will be divided by 0.9, because that is the 0.9. So, QC 0 is coming out to be here 15 into 10 to the power 3 kilonewton per meter square. Okay. Then QC1 that I have mentioned, it is the minimum value below the base of the pile up to twice d. So, here you can see twice d means up to 11.9. So, this 11.9, the minimum value of QC is 10,000 kilonewton per meter square or 10 megapascal, because that is the minimum value. Here also it is 10,000, here also it is 10,000. In this case, in other case it may be different, but in this case this is the 10,000. So, QC value will be 10 into 10 to the power 3 kilonewton per meter square. Now, the next one, which is the average of minimum penetration. Okay. So, that is very important. Okay. So, for that purpose let me do something, that it is up to 3.6. So, that is up to that distance is 3.6. So, that is 11 minus 3.6. So, up to that you have to consider. So, here minimum means that, so here first you draw, this is the minimum value. Okay. So, you draw this line. Okay, and there is another minimum value here. This is the minimum here. You draw this line also. Okay. So, now here average things will be calculated like this, that your QC2, the average of minimum value. So, here from 11 to this zone, this is the average. Okay, and that average value is 300 or that is 1, 2, 3, yeah, 3 megapascal. So, 3000. So, this is the average value from this point to this point. So, I am taking 3000 into that distance is up to 0.3. Okay, you can measure this distance from here to here. I have measured that, that is 0.3. 0.3 is this one. Okay, this is 0.3 meter. Fine, this one. Then from here to here it is increasing. So, you will take the average value of that. So, take the average value, that is 3000 plus here the value is 500. So, we will take this is 500. So, this is 500. And this thickness from here to here is 0.1 meter. This is 0.1 meter. Okay. So, I am multiplying it 0.1 meter, then plus now rest of the things, this 500 is the lowest value. Okay. So, I have to take 500 rest of the thickness. Now, if there is any lowest value within that 500, then you have to again go like this, because as the way I have proceed here. But here the next lowest value is the 500. So, what I will do, 500 and then the 0.3 and 0.1 I have already taken. So, that will be multiplied by 3.6 minus 0.1 minus 0.3. Okay. So, that will be 3.2, and then the total one I have to multiply, divide, that is divided by 3.6. Okay. So, that is divided by 3.6. So, QC2 will be equal to, in this case, is 743 kilonewton per meter square. So, now if I put these values here, that my QP2 will be, so that means if I put these values here, because now this point, this value is, this is 500 kilonewton per meter square. Okay. This value is 3000 kilonewton per meter square, and this is 10,000, this one 20, this is the 10,000. So, this way you have to do this analysis. So, this is 7.3 kilonewton per meter square. So, now if I put these values here, my QPU will be equal to 15,000 divided by QC1 is 10,000 divided by 2 plus 743 divided by 2. Okay. So, that is equal to 6621.5 kilonewton per meter square. Okay. So, that is I can write 6621.5 kilonewton per meter square, which is the similar kind of value that we got from the first method. Now, once you get QPU, then you multiply it with the area, base area, you will get the force, that is the tip resistance in terms of the force or the load, and then you have the average value for these things. Okay. So, now the last thing that I want to explain, that now the average QC you will get like the previous method. Okay. So, you take the average of the throughout the length of the pile, average QC value. Now, it is sand. So, that average QC value was coming out to be that for the first method, it was calculated that yes, that your Q average for 0 to 11 meter was 3642 kilonewton per meter square. Now, if you are taking this is in sand, so you can take this is the range. So, QC your Fs you can write that QC divided by 100 average. So, this will be 36.42 kilonewton per meter square. Okay. Then you multiply it, QS will be the ASFS and QPU will be AB by QPU. Then finally, you will get QU is QF plus QPU, and then this is QSAF will be QU divided by 2.5 is the factor of safety. So, this is the IS code method, because you take the average and then you take this limit. I am taking QC divided by 100, it is mentioned only sand. So, this is the limit, I am taking this 100. Okay. So, I will get this is the resistance 36.42. So, this is the way by which we can determine the load carrying capacity of the pile based on the SCPT value. Okay. So, next class I will discuss about the SPT value, how about the load carrying capacity of the pile based on the SPT value, and then I will discuss about the group load carrying capacity of pile. Thank you.